Okay, our first question is figure 11 shows a beam of radiation that contains alpha particles, particles, and gamma rays. The beam enters a very strong electrical field between charged plates in a vacuum. Indicate the deflection, if any, of the alpha, beta, and gamma particles by placing one tick in each column of the table. Let's start with alpha particles. Alpha particles will have no deflection. They will go towards the positive plate, negative plate. Will they go out of the paper or will they go into the paper? Hajra, what do you think? Where will the alpha particles go?
They'll go towards the negative plate.
Yes, correct. Good. Viraj, where will the beta particles go?
Uh, Positive.
Yes, correct. Shreya, where will the gamma rays go? Here you go, French fries. Shreya, where will the gamma particles go?
Is it no deflection?
Yes, gamma particles don't have a charge, so they do not deflect. This radiation, the radiation is said to be ionizing. Explain what this means. Viraj, what does the term ionizing means?
It has a charge.
Not exactly. I mean, gamma rays don't have a charge, but they are also ionizing. What does the term ionizing mean? Like when I say ionizing radiation, what do I mean? Because gamma rays don't have a charge, but they are also known as an ionizing radiation. Hajra, do you know what is an ionizing radiation? Or what is the meant by the term ionizing?
Not sure.
Okay. Shreya, any idea?
No.
Okay, ionizing simply means that when the radiation will travel through any medium, it will turn the atoms in its pathway into ions. That's what it means. Okay, that the radiation, the alpha particle, the beta particle, the gamma rays, when they will interact with the atoms in its pathway, it will turn those atoms into ions. So if it's traveling through air, then it will turn the air atoms into ions. Okay, that's what ionizing means, that you're literally taking an atom and turning into an ion. And your gamma, beta particles, and your alpha particles, they are all ionizing, meaning that they all have the ability of turning atoms into ions. Okay. Next, alpha particles are more strongly ionizing. So alpha particles will turn a lot of the atoms in its pathway into positive ions or negative ions and have a shorter range in air than gamma rays. Remember, I went over the differences between alpha, beta, and gamma rays with you guys. So one of the differences was that alpha particles are strongly ionizing, and that is why they have a shorter range. Gamma particles are weakly ionizing. They will ionize, but not as much as alpha particles, and they will have a longer range. Use your knowledge of the nature of these radiations to explain these differences. So we have to talk regarding nature of these radiations. So let's discuss. First of all, what is the nature of alpha particles? Does anybody remember from our last class? What is the nature of alpha particles?
They are highly ionizing and have weak penetrating power.
Yeah, Viraj, that's right. But what is their
That isn't.
nature? Remember, I told you guys that if you're
Isn't that the
asked about the
nature?
nature, no, no, no. I remember in the last class, I told you that if they ask you the nature, this is alpha particle, this is beta particle, this is gamma rays. What is an alpha particle? That is the property that it is strongly ionizing, low penetration, shorter range. Those are the properties. But what is an alpha particle? What is it in the first place? Hajra, Shreya, does anybody remember what is an alpha particle? Hajra, Shreya, does anybody know what an alpha particle is? What is an alpha particle? Alpha particle is the nucleus of, can somebody tell me? Nucleus of?
Or helium.
Yes, that's the nature. Nature is what is this thing? That's what it is. So alpha particle is a nucleus of helium. And what is the nature of gamma rays? Then tell me that, Viraj. What are gamma rays?
I don't know if it's correct or not. No, like gamma rays are electromagnetic waves.
Yes, exactly. Gamma rays are electromagnetic rays. What is a beta particle? Anybody knows what a beta particle is?
Isn't it like electrons?
Yes. The nature of beta particle is that beta particle is an electron. The nature of alpha particle is that it's the nucleus of helium. The nature of gamma radiation is that it is a electromagnetic wave. Aja, what is the nature of alpha particle? Hajra, can you hear me? Hajra, can you hear me?
It is a
Yeah.
nucleus of helium.
Yes, correct. What is a gamma radiation?
It is a electromagnetic radiation.
Correct. What's beta particle? Beta particle is a electron. Okay. Alpha particle is a nucleus. Beta particle is an electron, and a gamma rays are electromagnetic waves. Shreya, what is an alpha particle?
An alpha particle is a helium.
Yes, correct. What's a beta particle?
Electrons.
Yes, and what's gamma radiation?
Electromagnetic waves.
Yes, correct. Now, everybody, make sure we remember this. Now, they're saying we have to use the nature of these radiation to explain the differences, meaning that we have to explain why alpha particle is strongly ionized. The reason alpha particle is strongly ionizing is because alpha particle is a nucleus of helium. Since it is a whole nucleus, it is quite large, isn't it? So when it's traveling through air, for example, is it not going to just bump into everything in its pathway? Right? Like, think about it. It's a whole nucleus of helium. It's going to bump with every single thing in its pathway. And when it will bump into every single thing in its pathway, it will ionize them. It will turn them into ionizing. It will greater mass plus charge. It also has a greater charge. So it is going to do greater ionization. Since it is going to do greater ionization, it will lose its energy. It will quickly lose all its energy. And since it will lose all its energy, it will only be able to travel a short distance. On the other hand, gamma rays are electromagnetic waves. Since they're electromagnetic waves, they are easily able to pass through the air or your paper, aluminium, whatever, with because they're very small. They're electromagnetic rays, right? So they can easily pass through without colliding or interacting with the atoms in its pathway. So it is going to do less ionization. So it will lose less energy. So it is able to travel over great distances. Right? Is that making sense? Everybody understands the concept between alpha particles and gamma rays?
Yeah.
Ajra, Shreya, making sense?
Yes.
Shreya, got it?
Yeah.
Okay. Now, a technician sets up a radiation detector in a university laboratory for use in some experiments. Even before the radioactive source for the experiment is brought into the laboratory, the detector registers a low count rate. Suggest what causes this count rate. They're saying that even before he brings the detector into the laboratory, even before he brings the detector close to the source, close to the radioactive source, the detector is still giving it a low reading. What is this low reading? Even if there is no radioactive material around you, you will still get a low reading. What is that low reading? Hajra, can you tell me what that low reading will be? Viraj, can you tell me what's this low count?
Is a background radiation.
Yes, it is background radiation, right? Background radiation is the low radiation that is always present all around us, right? It comes from your radioactive rocks, your volcanoes, from the space. There is constant low level radiation all around us. Now, the radioactive source that emits alpha particles is placed on the laboratory bench, and the source is gradually moved close to the detector. Okay? At first, the detector continues to register a low count rate. Okay? Sometimes slightly less than the count rate registered without the source. So, as he's bringing the detector close to the source, he is getting a low count rate. In fact, it is even sometimes it becomes lesser and then becomes larger again. Then the count rate suddenly increases to a very high value when the source is very close to the detector. Explain these changes in the count rate. First of all, can somebody tell me this? Why is the count rate suddenly shooting up when the source is close to the detector? Shreya, can you tell me why do you think the count rate on the GM tube or the count rate in the detector, why is it suddenly shooting when I bring the counter close to the alpha particle source?
I'm not sure.
Think about it, Shreya, that these are alpha particles that are being emitted from the source, right? So alpha particles have what is the range of alpha particles? Do they have a long range or a short range?
I think Sean.
Yes, they have a short range. You're right. You're right. They have a short range. So if they have a short range, then I will not be able to detect them from far away, right? I will only be able to detect them when I get close to the source, right? That makes sense.
Yeah.
Okay. So the reason the count rate is suddenly increasing is because now I'm close to the source. So I can actually detect the alpha particles. Okay. Now, the next question of mine is that, Viraj, they are saying that the detector continues to register a low count rate, sometimes slightly less, meaning that the count rate is not constant. Sometimes it becomes a bit more, sometimes it becomes a bit less. This is the tricky question. Viraj, why do you think this is happening? We are not close to the source right now. Okay, we're not close to the source right now, we are far away from the source, right? When we will get close to the source, we will detect the alpha particles and the radiation level will shoot up. But When I am bringing it slowly towards the source, I have my background radiation showing up on my detector. That is fluctuating. Why is it fluctuating, Viraj?
Okay, so mm, uh, so at first, yeah, when the detector is like a bit far away from the source, yeah,
Yeah,
and since alpha particles have a limited range,
yeah,
like a few centimeters, yeah, so they're
yeah.
probably gonna get like absorbed in the air, and they couldn't
Okay,
probably reach the detector, and some might, so
okay,
like that's why it has a low value at the start, and then as the detector moves close, yeah,
yeah.
uh uh it might be in the range and like it can detect it now.
That's fine. That is correct. But why is it that it's fluctuating? They're saying it becomes slightly less, sometimes slightly more. Why do we see the fluctuation?
They might not have the energy.
Okay, no. It is because, do you guys remember what did I tell you? I told you guys radioactivity is a random process. Do you guys remember that? I told you radioactivity is a random process. It happens randomly. That's the reason. So sometimes we get a high value, sometimes we get a low value. Okay, so small fluctuations happen because radioactivity is a random process. Okay, and as we will get close to the source, as I will get close to the source, I will detect the alpha particles and the count rate will shoot up. Okay, you guys should be able to do this. A technician sets up a radiation detector in a university laboratory for use in a class experiment. A radioactive source that emits beta particles is placed on the laboratory bench 10 centimeters from the detector. A small count rate is registered. State the name of the particle found in an atom that is identical to beta particle. Hajra, what is the particle that is identical to beta particle that we find in an atom? You know the answer to this.
So is it asking what is inside the beta particle?
Yes. Yes, it's asking you what is a beta particle. Exactly. So what is a beta particle?
Uh, it's made of a tritium.
I'm sorry, I couldn't hear you. Can you say it again? It's made of, it's what?
Um,
We
is it
just
made up of
discussed this.
tritium?
Electron?
Oh,
Yes, beta particle is an electron, right? That's your answer. Okay. Electrons are also found in an atom. So beta particles are electrons. That's it. That's all you have to write down over here, electrons, because the nature of beta particle is that they are an electron. Next one. Technician sets up his shale equipment in the same way every year. Okay. He notices that the count rate registered by the detector every year is slightly smaller than it was the previous year. So last year he got a larger value. This year he's getting a smaller value. Then when he does it again next year, he gets an even smaller value. Year after that, again a smaller value. Suggest why this is so, Viraj. Why is this happening? Why is it that every year the count rate is decreasing?
Wait, so the distance is the same,
Distance is the same. He sets it up in the same exact way every year.
but isn't the radiation random? Yeah.
Okay. Randomness is what we use to explain fluctuations. This is not a fluctuation. Every year it is decreasing. It's not a fluctuation that's going low and high, low and high. Every single year, the radiation is constantly decreasing. Why?
Oh wait, so this time it's beta particles, yeah. It's
Yeah,
not alpha
yeah.
particles. Okay,
No.
so
If anybody else can think of the answer, Hajra, Shreya, please. Every single year, the radioactivity is decreasing. The count is decreasing. Why is the count decreasing? Viraj, every single year, the radioactivity is decreasing. And I know you know this. Every single year, the radioactivity is decreasing. Why is the radioactivity decreasing every single year? Because of, you know this. You know this. It's a radioactive source. It does not matter if it's alpha, beta, or gamma. For every radioactive source, the radioactivity decreases over a period of time. Remember? Every single source, for every single source, radioactivity decreases over a period of time. It is known as, Raj, think of it. I know you know it. Radioactive decay, right? Every single radiation source, the radioactivity decreases over a period of time. We call it radioactive decay. We even studied the graph for it. The graph goes like this. Sorry. The graph goes like this. And we studied about it half-life, the time taken for the radioactivity to decrease by half. Right? So this is why is the count decreasing every single year? Because of radioactive decay. What is radioactive decay? Breakdown of the radioactive source, right? And as the radioactive source is going to break down, the count is going to decrease over a period of time. The time taken for the radioactive count to decrease by half is known as half-life. This is why this is why, Viraj, see, this is not fluctuation. Fluctuation is due to random nature. Yes. But this is not a fluctuation. Every single year, the count is decreasing. Every single year. It's just getting lower and lower and lower and lower. Why? Because radioactive sources decay. They break down. Their count decreases. That's why the count is decreasing. Got it? Making sense?
Yeah.
Hajra, Shreya, is this making sense?
Yes.
In the second experiment, the same equipment is set up, but a radioactive source that emits alpha particle is placed 10 centimeter from the detector. The same number of particles are emitted every second from this source as were emitted from beta source. Explain why the count rate obtained is much lower. Shreya, I am putting the detector at the same distance. Okay, but with alpha particles, I am getting a lower count rate at the same distance as the beta particle. Why?
Because the alpha particles, like they travel, like the
Yes.
distance that they travel is shorter. So
Yes.
yeah.
Correct. They travel a shorter distance, so less alpha particles will reach the 10 centimeter mark compared to the beta particles. Absolutely correct. Okay, a technician sets up a radiation detector in a university laboratory for use in some experiments. Even before the radioactive source for the experiments is brought into the laboratory, the detector registers a small count rate due to background radiation. Suggest one source of this background radiation. Ajra, can you think of a source? Where does the background radiation come from? Ajra, can you give me any source of background radiation? There is constant radiation present all around us. Where is it coming from? Any one source.
From the earth.
Yeah, from the radioactive source, rocks in the earth. Okay. You have to be a bit more specific. From the radioactive rocks inside the earth, from the radioactive gases inside the earth, from
Can it
our
be soil as well?
volcanoes. Sorry?
Can it be soil as well?
Yeah, correct, fine. And then it is also going to come from the stars that are present in our universe. Okay, that's good. Okay, next they're saying the radioactive source emits gamma rays. It is placed on a laboratory bench close to the detector. State what gamma rays are. Shreya, what are gamma rays?
The electromagnetic waves.
Right. And can you, since this is for 2 marks, so can you just add about the charge and mass over here as well?
Gamma rays have no charge.
Yes. And they have also no mass. Okay, they don't have a charge and they don't have a mass. A lead sheet of thickness 10 millimeter is positioned between the detector and the radioactive source. State and explains what happens to the count rate on the detector. What do you guys think? I have a radioactive source that produces gamma rays. I place a lead sheet between the detector and the source. What do you guys think will happen to the count rate of the detector? Viraj, what will happen and why?
It's gonna decrease because
Mhm.
the lead is gonna stop the gamma rays from passing through.
Yes. It will absorb some of the gamma radiation, so the count rate will decrease. Correct. In a second experiment, gamma rays pass through the air to the detector. One end of the bar magnet is brought close to the path of the gamma rays. Tick one box to indicate the effect on the path of gamma rays. Hajra, where will the gamma rays go if I bring a magnet over here?
I think there will be no deflection
Correct. Explain your answer. Why will there be no deflection?
because gamma rays don't have any charge.
Correct. Or any mass. Okay. Complete the following statements. An alpha particle consists of Shreya. An alpha particle has what?
Helium. Actually, no.
Right. And can you tell me how many protons and neutrons?
They have two protons and two neutrons.
Correct. Very good. And a beta particle consists of a?
It consists of electrons.
Yes. Very good. Correct. As alpha particle and beta particle pass through a gas, the molecules of the gas become ionized. Explain what is meant by ionization. Hajra, what does ionization mean? Hajra, what do we mean by ionization?
It's when an atom gains a positive or negative charge by losing or gaining electrons.
Yes, correct. Very good. Figure 11.1 shows the beam of alpha particles and a beam of beta particles. The beams are about to enter a region of a very strong magnetic field. The direction of the magnetic field is into the page. Suggest why parts of the particles in the magnetic field are curved. Viraj, can you tell me?
Because both the particles contain a charge
Right. And they will experience a force
from the magnet.
perpendicular. Yeah, they will experience a force pulling them upwards or downwards, whatever.
Wait,
That's why.
like
Yeah.
the question says that the direction of the magnetic field is into the page.
Yes. Yes, Viraj.
So where will the force act then?
The force, all of them have to be perpendicular to each other. So if the magnetic field is, that's the principle of electromagnetic radiation, or sorry, electromagnetic induction, right? Whenever we follow our left hand rule or right hand rule, all three of these are mutually perpendicular to each other, meaning that force and your magnetic field and your current. If you open your hand right now, for example, open your left hand in the left hand position, you will notice that all your fingers are at 90 degrees to each other, aren't they? None of them are parallel. They are all at 90 degrees with each other. The principle of electromagnetic induction or the motor effect. This principle only works if all three of these are mutually perpendicular, meaning that all three of them are at 90 degrees to each other. If the magnetic field and the current are in the same direction, it will not work. If the force and the magnetic field are in the same direction, it will not work. That is why, for example, if I give you the example of a motor, okay? So that is why when you are moving your motor in a magnetic field, Viraj, the magnetic field is like this, but I will rotate the motor up and down, right? If I move the motor left and right, will anything happen? If I talk about a generator, if I move the generator left and right, will I see anything? No. The generator has to rotate. It has to go perpendicular. So if the magnetic field is horizontal, the force has to be vertical. So the generator will rotate accordingly, right? So the reason for this is because if you remember what was the principle, that there is cutting of the magnetic field lines. Remember, Hajra, I've not done this with you, but I will cover this with you. Viraj and Shay, remember, cutting of magnetic field lines. So they have to be perpendicular and 90 degrees to each other. If they are in the same direction, will we see any cutting? No. Remember this, force, magnetic field and current, always perpendicular to each other, all at 90 degrees to each other. Okay, so if the alpha particles are left to right and the magnetic field is going into the page, so the force will either be up or down. Okay, Viraj, making sense now?
Yeah.
Okay, now you guys have to figure out where will the alpha particle and the beta particles go. First of all, Shreya, should I use my left hand rule or my right hand rule?
Left hand.
Good, correct, left hand rule. So, Hajra, what will be the direction of my first finger? Hajra, what will be the direction of the first finger?
For which particle?
For alpha particle. For both alpha and beta particle, the first finger will be the same.
On the right side.
The first finger represents the magnetic field. And where is the magnetic field acting? I highlighted it in the question. Where is the magnetic field acting?
Into the page.
And so your first finger will point where?
Onto the page.
Into the page. Good. First finger, you guys, is going to point into the page. Viraj, where should my second finger point?
I think where the alpha particle goes through,
Yes, so alpha particle is traveling in which
from
direction?
left
Left or
to
right?
right.
Right. So
Like
our
right,
second
yeah.
finger will, our second finger will point to the right hand side.
Yeah.
First finger will point into the paper. We are using the left hand. Shreya, where is your thumb pointing?
Upwards.
Very good. Correct. Now, for the beta particles, you guys can try to figure it out using your hand. Okay? Or just remember one trick. Alpha and beta particles are always opposite to each other. So, if the alpha particle is going to go upwards, the beta particle will go downwards. Okay? That's how you can figure it out. Figure it out for the alpha particle, and the beta particle will always be opposite to it. Okay? In a laboratory experiment, the isotope of uranium-238 is used as a source of alpha particles. State one feature of uranium-238 nuclei that is the same for the nuclei of other uranium isotopes. Hajra, what will be the same between this isotope and the other isotopes? Hajra, can you tell me what will be the same between this isotope 238 and other isotopes of uranium?
Is it going to
Okay,
be the numbers of protons to be
good,
different?
correct.
Yeah.
Yes. Proton number is going to be the same. So isotopes have the same proton number. And what will be different? That's part
And the
B.
neutrons will be different?
Exactly. Correct. Good job. Well done. Okay. Never mind. This is not anything. In a laboratory at a nuclear power station, a radiation detector is connected to a computer. The readings recorded are displayed on the computer screen. The detector is switched on. 10 minutes later, at time t is equals to 10 minutes, a small sample of radioactive material is removed from a nuclear reactor and placed near to the detector. Okay, so what are they saying? That we have switched on a detector. Okay, then at 10 minutes, they have taken a sample of the radioactive material and put it in front of the detector. Then they record the readings for 40 minutes. Use figure 11.1 to determine the background count rate in the laboratory. Shreya, by looking at this graph, what do you think is the background count rate?
Don't know.
Okay, no problem. Shreya, I will help you. Background radiation is the low level radiation that is always present. Okay, now look, they are bringing the radioactive material at time t is equals to 10 minutes, right? But so that means when is the radioactive material coming? At time 10 minutes. But you can see that even before 10 minutes, there was some radioactive count that was present, right? Can you see that on the graph? That even before 10 minutes, even before I bought the radioactive material, there was still a low level count that is present on the graph. Can you see it? Shreya, can you see it?
Yeah.
You just need to read the value from the graph. Can you read this value from the graph? Before 10 minutes. See, before 10 minutes, there is still some radioactivity that's present. So the question is this, that we did not bring at 10 minutes, I brought the radioactive material. Before 10 minutes, there was no radioactive material. So why do we have this radiation? This is the background radiation. So you will just read the graph. Can you please read the graph for me?
Is it 12?
Yes, good job. Correct. You simply need to read the graph. See the stationary line? Before we bring the source, whatever reading is there, that's your background radiation. So it's 12. Use figure 11.1 to determine the count rate due to the radioactive sample at time t is equals to 10 minutes. Hajra, at time t is equals to 10 minutes, what is the radioactivity count due to the sample? Due to the sample, what is the radioactivity count at time t is equals to 10 minutes? The graph is in front of you.
I'm not sure, but is it going to be 72?
Yes. 74. This is 84.
Oh,
Okay. But
okay.
yes. No, you are right. You're right. 74. 72. Correct. You are absolutely correct. So over here, we can see that at time 10 minutes, we have 84. Okay. The background count is 12. So to find the count of the sample, we will subtract. 84 minus 12 will give us 72. Good. At time t is equals to 19 minutes. Viraj, what's the radioactivity count at 19 minutes?
Is it like 20? Like it's near 20, yeah.
Yeah, like 21 probably,
21,
right?
yeah. 20.5 something like
Yeah, I think it's 21 because then this is 22, so it's like in the middle, so probably 21. Okay. Now they're saying use the values obtained in B to estimate the half-life of the radioactive sample. You guys have to figure out the half-life of the radioactive sample. The starting count is 72. Okay. So after one half life, what will be the radioactive count? Hajra, can you tell me? When one half life passes, what will be the radioactive count? At the start, it is 72. Or
36.
1 second, sorry. Let's take 84 because it'll be easier to read it from the graph. Let's take 84 because we can read it from the graph easy. So what will be after one half life?
42.
42. So read from the graph and tell me how long does it take for the radioactivity to decrease to 42. Can somebody read the graph and tell me how much time did it take for the activity to decrease to 42?
Will it be 18 minutes? No, or
No. Try it.
14.
I marked it as well just so it's easier for you to read.
So it'll be 14.
Yes, 14. Correct. And 1 second. Just give me 1 second. Hold on. I think maybe I might be missing something. All right, I think this is fine. Okay. Now, after that, they are saying to us, 1 second. In a research laboratory, a radioactive sample is placed close to a radiation detector. The graph in figure 11.1 shows the decay of the sample. After 6 decays, the count rate hardly decreases and in fact increases a little at time. Explain these observations, Viraj. They're saying after your 6 days are already passed. Okay, so they're saying that it stops decreasing, it doesn't decrease anymore, and in fact at times it also fluctuates, it increases a little bit. Why do you think this is happening?
Uh, I think it increases at a little times because radioactivity is random.
Yes, that is why it decreases randomly, because it's a random thing. And why does it stop decreasing after 6 days? The reason for that is because the radioactivity count must be now quite close to zero. Okay, the radioactivity count is quite close to zero. Like the sample has almost completely decayed. The radioactivity count is so low that we cannot see the changes in it anymore. Okay, that's why. Because think about it this way, that for example, if you have 0.1, then the half of 0.1 is 0.05. Half of that is 0.0025. Half of that is 0.000125. Right? So when the radioactivity gets very close to zero, it's hard to observe it. It looks almost the same. Okay, so it's still decay is still happening, but it's just that we cannot see the decay that much because the count is so close to being zero. Use the graph to determine the half-life. How are we going to figure the half-life? What is the initial count, Hajra? Can you read the graph and
52.
tell me what the initial count is?
52.
52. Correct. Now we have to figure the half-life. So in the first half-life, the count will decrease to what?
26.
26. Yes, correct. So can you tell me what the half-life will be? Actually, 1 second. Sorry, 1 second. Let me ask you something, Hajra. Over here, you can see that even when the radioactive decay becomes zero, or even when the radioactive sample is almost all gone, we still have some low-level radiation. What is this low-level radiation? Shreya, can you tell me what is this low-level radiation? That even after all of this sample has decayed, we still have some radiation left. What is this low-level radiation?
Is it background?
What? Correct. Correct. So the count over here, Shreya, we're getting is 54. So we have to always subtract what? We have to subtract the background radiation. So can you read the background radiation from the graph first? Can you read the background radiation from the graph?
The background radiation will be 14, right?
Right, background radiation will be 14.
Hmm.
Okay, anyway, so Hajra, continuing from where we had left off, 54. The half of 54 will be 26. So from the graph, 26 will be how many days?
Around 3 days.
Yeah, it's going to be around 2 days. Okay, all right. Just give me 1 second. Let's move on to the next question. Okay. After that, they're saying to you another radioactive sample is a strong emitter of alpha particles and gamma rays. A junior researcher suggests that with sufficient safety precaution when working with the sample would be to hold the sample with long forceps. Explain why this suggestion, although helpful, may be insufficient. Viraj. They're saying that we have a radioactive source that produces alpha particle and gamma rays. So someone has suggested that, you know what, if we hold the sample with long forceps, that should be good enough. Why do you think that this is not sufficient?
Wait, what is a forceps?
Tong. It's a tong. You know, like forcep a tong. So remember how I
Oh
taught
yeah.
you that, yeah, we discussed that we never lift radioactive materials with hands. We use a forcep or a tong. So that's what it is. What do you think? Why is it that, yes, it's helpful that if you hold it with forceps, but it's definitely not sufficient precaution? If anybody else can think of the answer, Hajra, Shreya, you can speak up as well.
Is it because like since like alpha particles, yeah?
Yeah.
Maybe like the distance might be not that long.
Okay, so then this should be good enough, right? If I follow your logic, alpha particles travel a short distance. So if I hold it with forceps, then I'll keep them far away from each other and I should be safe.
Yeah,
But the
but
examiner is
that doesn't
asking this is
happen
not
with the
with the,
gamma rays, right?
yes. Yes, exactly. So your answer will be over here that alpha particles, yes, they only travel a short distance. Okay, so holding the source with a tong or a forceps will be really nice and helpful because we can keep it far away from us. But gamma rays can travel over long distances. So even if you hold it with a forceps, that is not going to keep you safe. Okay. A radioactive source emits alpha, beta, and gamma radiation. Which of these radiations has the shortest range in air? Hajra. Which of them, alpha, beta, gamma, will have the shortest range in air?
Alpha.
Correct. Has a negative charge, Shreya?
Beta.
Shreya, the second one. So say it again, sorry.
Is it beta?
Yes, beta. Is not deflected in a magnetic field, Viraj?
Gamma.
Yeah. Okay. Last question for today. 6 different nuclides have nucleon and proton numbers as given. I want you to guys to do part B. Thorium-232 has a half-life of 1.4 into 10 raised to the power of 10 years. At a particular instant, the activity of sample of thorium-232 is 120 BQ. Calculate the time taken for the activity of the sample to fall to 15 BQ. You guys have 2 minutes.
Wait, so like, it's 1.4 times 10 to the power of 10, yeah? And like, which
Yes.
equals like 120 BQ. So do I like half it?
Half what?
That's the question. Like, what
This
should I have?
Viraj, this is the number of years, meaning that this is the half life, meaning that it takes 1.4 into 10 raised to the power of 10 years for the radioactivity to half. Think about the definition of half life, right? Half life is the time taken. This is just the time that it will take 1.4 into 10 raised to the power of 10 years for the radioactivity count to half. So what do you have to half?
Uh, Years, I think. No,
No. Years is the time taken. This is how long it will
the
take.
120 BQ.
Yes, exactly. This is the just the time, Viraj, that it will take this much time for the radioactivity to half. What is the radioactivity? This. Okay, so you have to half the radioactivity, not the time.
Yeah, but like, okay, so
Yeah.
if I divide this by 2 like 3 times, okay. So like
Yes.
120 divided by 2 divided by 2 and divided by 2, I get 15. So I get 3
Yes.
twos. Does that mean like
Yes. Three half
so
life.
like
So
so
you
does
get
that
three
mean I
half
have
life.
3 half lives, yeah?
Yes. So what is the time for one half life? How many years is one
1.4
half?
times
Yes.
10 to the
So
power of
just
10
multiply this by.
times 3. Yeah,
Just yes times 3. Correct.
4.2 times 10 to the power of 10.
Yes, that is correct. Hajra, Shreya, are you guys getting the answer? Do you want me to go over the question with you guys?
Yeah.
Take another minute. See if you guys are getting the same answer. If you guys are getting the same answer, or if not, let me know. I will discuss it with you.
So the half-life is it's going to take 3 half-lives to
Yes,
decrease to
it's
15.
yes, correct.
So
It's going to
then
be
do you
three half
multiply it 1.4?
lives. Yes. So it's going to be three half
So
lives. So
so
120.
1.4 multiplied by
Yeah.
3?
Go on, go on. Yes. So
Okay.
we will get three half lives, right? From 120 to 60, then 60 to 30, and then 30 to 15. So we're getting three half lives. One half life is this much, 1.4 into 10 is to the power of 10. So how many half lives do we need? Three. So just multiply. That's it. Okay. So we need three half lives for the count to get to 15. But for one half life is 1.4 into 10 raised to the power of 10. And we have three half lives. So 3 multiplied by 1.4 will give you 4.2 into 10 raised to the power of 10. So this is how many years it will take for it to get to 15 BQ. Making sense to everyone, right? Shreya, I hope this is making sense.
Yeah.
Okay, perfect. All right, good job, everyone. So we'll go ahead and stop it over here for today. And now in our next class, we are going to start off with our topic of